The topic of other worlds existing outside our universe often arises in scientific and not-so-scientific fiction. But is something like this possible in reality? And more specifically, how does this concept fit into our modern understanding of physics? This is a complex and interesting question without a definitive answer. Moreover, many physicists consider discussions on this topic unscientific, as they see no way to test and confirm or refute the existence of other universes, and thus they argue it is pointless to spend time discussing this topic. However, one cannot simply forbid scientists from thinking about something, and at the moment there are many theories that one way or another touch upon the question of parallel universes. One of the most well-known concepts that inspires many theorists of the multiplicity of worlds is the so-called many worlds interpretation of quantum mechanics, proposed in the late 1950s by American physicist Hugh Everett. The key feature of quantum mechanics is that it does not provide exact solutions. When asking whether a certain event will happen over a period of time, in quantum mechanics, you can never get a yes or no answer, but always speak only of the probability of it happening. This is not due to the imperfection of quantum mechanics, but to the properties of the objects it describes. A classic example is the radioactive decay of unstable atomic nuclei. Suppose we have a box in which we place 20 atoms of ruthenium-106 with a half-life of about 1 year. This means that, opening this box in a year, we will most likely find only 10 atoms of ruthenium-106. The remaining 10 will have undergone beta decay, turning into rhodium-106 atoms. We can be somewhat sure that events will unfold this way. However, it will be impossible for us to predict which atoms will decay and which will not. Conversely, we cannot say when exactly a particular atom will decay. It could happen in a second, a day, a year, or even not at all for 10, 100, 1,000, or 1,000,000 years. How to explain this fundamental uncertainty of quantum mechanics? Everett proposed his many worlds concept for this purpose, according to which any possible outcomes of certain quantum measurements are realized, but just in different universes. In other words, if an observer, opening the box with atoms, finds such and such a picture of decay results, then in another world, a quantum copy of this observer will find a different picture, and in a third world, the picture will be like this, and so on. Everett's parallel worlds live by the same physical laws, but the specific results of specific physical processes in them differ, which means that the course of events in these worlds will differ. And if you recall that everything in the universe, from stars and galaxies to us, consists of quantum objects, and the entire evolution of the universe, human history, or the biography of a specific person ultimately represents a huge number of successive events at the quantum level, then Everett's concept literally predicts the possibility of parallel worlds where Hitler remained an Austrian artist and the Titanic did not sink, or vice versa, worlds where Homo sapiens did not arise, or Earth itself did not form. However, Everett's concept does not tell us what these worlds physically represent, where they are located, whether it is possible to enter them or at least somehow contact them, and most importantly, how exactly they are formed. This was not required of it, as Everett did not set out to describe the physics of multiple worlds, but created an interpretation of quantum mechanics, that is, a way to visually present the work of its laws and principles. Nevertheless, other scientists, including those inspired by Everett's reasoning, have focused on the problem of other worlds more specifically. When modern physicists, especially astrophysicists and cosmologists, say the word universe, they usually mean the observable universe, that is, the volume of space accessible to our direct observations. This volume is definitely limited, and beyond it, there could easily be something else. Here's why. According to our modern understanding, the universe as we know it originated at a specific moment in the past. We believe today that this happened about 13.8 billion years ago. We also know that nothing in the universe, at least in our observable universe, can move faster than the speed of light in a vacuum. These considerations outline the boundary of the observable universe, beyond which are objects fundamentally unobservable to us, because the light or other signals emitted by them simply did not have time to reach us in the entire existence of the universe. This imaginary boundary between the observable universe and its more distant parts is also called the cosmological event horizon or the particle horizon. And everything beyond this horizon, from our point of view, can be considered another universe. The cosmological event horizon is an imaginary surface. There is no physical boundary between the observable and unobservable universe. Moreover, if we consider a point in space far from Earth, the boundaries of the observable universe will be different. In essence, for each point, there will be its own observable universe and its own other universe beyond its boundaries. And furthermore, the boundaries of these observable universes can change over time. On the one hand, over time, signals from more and more distant sources should reach the observer at the center of such a universe. On the other hand, over time, space continues to expand, so distant sources become more and more distant. Depending on how the expansion speed of the universe changes, two scenarios are possible. If the expansion of the universe slows down, as was believed until relatively recently, the boundaries of the observable universes, including our own, will expand, revealing more and more previously invisible objects to the observer. If, as most modern scientists believe, the expansion speed of the universe increases, the opposite process will occur. Objects currently observable in the universe will gradually move beyond the cosmological event horizon, ceasing to be visible and becoming part of the other universe. This theory is good because it is most likely true, in the sense that it fully fits all the physical laws known to us today and does not require any additional assumptions. True, we cannot say for sure that there is really something beyond the observable universe, since by definition we cannot look beyond the event horizon. But in terms of possibility, yes, it is certainly possible and even quite likely. However, this hypothesis has its drawbacks, the main one being that it is simply boring. The space of the unobservable universe should live by the same physical laws and be in everything similar to our observable universe. You cannot cast an Avada Kedavra there, nor will midichlorians settle inside you. And generally speaking, can we consider what we talked about above as another universe just because we do not see and cannot reach this other universe? And if we can someday, then what? In general, yes, I understand if my viewers say that this is not other universes, but just very distant parts of our own. Fortunately, modern physics has theories that are more interesting, and one of them is related to the hypothetical process that supposedly took place in the early universe, the so-called cosmic inflation. The hypothesis of the inflationary expansion of the universe suggests that shortly after the Big Bang, the universe experienced a period of rapid increase in its volume. Approximately within 10 to the 36 seconds, its radius grew at least by 10 to the 26 times, or by a trillion times. During such an expansion, the separation speed of points in space significantly exceeded the speed of light. After this burst of space expansion, inflationary expansion ceased, replaced by normal Hubble expansion, which we observe today. The concept of inflationary expansion was devised by physicists to explain a number of phenomena observed in the modern universe, and in this regard, it copes well with its task, but it has several problems. For example, we have no idea about the mechanism that controlled the inflation, why it started, and importantly, why it stopped. One of the models designed to explain this is the model of the so-called scalar inflaton field, supposedly present in the early dense and hot universe. The existence of this field caused cosmic inflation, but as this process developed, the energy density of this field rapidly decreased, and once it became so low that inflation stopped. However, we cannot be sure that this very density of the inflaton field, whatever it may be, was the same in all points of the universe. On the contrary, quantum mechanics forces us to assume that most likely, this density could significantly vary in different points of the universe, including due to so-called quantum fluctuations. In other words, the conditions for the end of inflation could arise at different points in the early universe at different times. For example, in the area of space known to us as the observable universe and its surroundings, this process could have stopped, while in other areas of space it could still be ongoing. And moreover, theoretically, somewhere in the universe, inflationary expansion can continue even today. This version of the hypothesis of cosmic inflation is also called the hypothesis of eternal inflation. According to it, the multiverse can represent a multitude of bubble universes of various sizes, arising at different times during the inflationary expansion, and still separated by the sea of inflationarily expanding space. And since the speed of this inflationary expansion is very high, the bubble universes cannot communicate with each other in any way, since the signals coming from them can travel through the space separating them only at the speed of light, while this space itself expands much faster. That is, these are already truly different universes, not connected to each other in any way. However, I'm not sure they can be called parallel, since they are separated by almost ordinary space, just expanding according to rather unusual laws. This theory also fits well with our modern cosmological views, but it has its own problem. The concept of cosmic inflation itself is only a hypothesis, which so far lacks experimental and observational evidence, and as for the hypothesis of eternal inflation, a special case of the more general inflationary hypothesis, it's even more speculative. Moreover, we cannot, and most likely will never be able to, definitively know whether these other universes, separated from us by the bottomless chasms of rapidly expanding space, exist. Even if we obtain evidence that inflationary expansion did take place, which scientists are actively working on, and there are some interesting ideas in this direction, it still wouldn't confirm the hypothesis of multiple bubble universes. However, even in our immediate vicinity, there are objects that, with some stretch of the imagination, can also be called other universes. These are black holes, or rather, the regions of space enclosed within their event horizons. What do they have in common with parallel worlds? For example, the impossibility of obtaining any information about what happens there from our world. That is, a black hole kind of bites out a region in our space that can quite aptly be called another universe, though only halfway, because unlike a real other world, hypothetical inhabitants near the black hole's space can observe our world, although they cannot influence it. We, on the other hand, cannot observe what happens inside the black hole, but we can influence, or at least try to influence, what occurs there. But what if our universe, as we know it, is also inside a black hole? It sounds like nonsense, but it is not that impossible. According to calculations, the mass of the observable part of the universe is around 10⁻53 kilograms. A black hole of such mass would be about 10 billion light-years across, which, order-wise, is precisely the size that the observable universe might have, according to our current understanding, and some physicists believe this cannot be a mere coincidence. This hypothesis sounds quite exotic, as we are used to thinking of the space inside a black hole as something where life as we know it is impossible. However, this concept does not contradict, for example, general relativity. According to it, the space inside a sufficiently massive and large black hole will not differ significantly in its properties from the ordinary space we are used to. So if our observable universe is inside a giant black hole, why shouldn't other such black holes exist in the multiverse outside this black hole, each containing its own world? These worlds might even communicate with each other via wormholes passing through the centers of such black holes. Theoretically, such objects are possible, though scientists still debate whether material objects with mass can travel through them. Perhaps the farthest in the reasoning about other worlds inside black holes went the American astrophysicist Lee Smolin. He suggested that the formation of any black hole, including those we observe in the surrounding cosmos, is essentially the birth of a new universe inside an existing one. According to Smolin's theory, the multiverse thus represents not just a multitude of worlds, but a peculiar hierarchy, with numerous black holes at each level, each containing numerous black holes, which are separate worlds. According to Smolin, these worlds can both form and perish in a process somewhat similar to natural selection. The idea of a multiverse consisting of numerous worlds inside black holes is already reminiscent of what we read in science fiction works, but it has certain inconsistencies with our physical understanding. For example, as far as we know, the space of our universe is largely homogeneous and isotropic, meaning that in different parts of this space, all physical processes occur the same way, and all possible directions in this space are equivalent. Whichever way we look, we see roughly the same. For the space inside a black hole, this is not true, as there definitely exists a preferred direction toward the center of this black hole. And as we approach this center, the properties of the space and all processes occurring in this space should change. An attempt to resolve this contradiction is the idea proposed in 2014 by Canadian physicist Robert Mann. He suggested that the black hole in which our universe is located is four-dimensional, and what we perceive as the three-dimensional space of our world is merely the closed surface of the event horizon of this black hole. This is similar to how the event horizon of an ordinary three-dimensional black hole is a two-dimensional sphere, an object with a dimensionality one less than the dimensionality of the object that generated it. So here, a three-dimensional hole generates a two-dimensional event horizon, and a four-dimensional one generates a three-dimensional event space, which we call our universe. And this three-dimensional space, each point of which is at the same distance from the center of the black hole, can very well be homogeneous and isotropic, which is what we observe in reality. In general, the idea is that the three-dimensional space of our universe is curved and closed in some fourth dimension, or a system with even higher dimensionality, are quite popular among astrophysicists and cosmologists, even without any connection to black holes, as they allow for a relatively simple visualization of the infinity of the universe, or at least the absence of an edge or boundary to the universe, even with a finite mass or volume. Indeed, from the point of view of an Earthling, its surface is also infinite in the sense that no matter how far we walk in any direction, we will never reach something that can be called an edge. However, in three-dimensional space, the Earth has a finite volume, surface area, mass, and so on. So here too, the seemingly infinite three-dimensional space of the universe might turn out to be quite finite in a higher dimensional space. And in this higher dimensional space, many such objects, separate universes, can coexist. The coolest part here is that the theory of three-dimensional bubbles in a higher dimensional space can theoretically be tested, or at least attempted to be tested. Although we, as three-dimensional beings, cannot look into what is happening in four-dimensional space, or even less travel through the fourth dimension to other universes, we can theoretically determine if our native three-dimensional space is curved in a higher dimensional space. The logic here is approximately as follows. If we draw a triangle on a plane, the sum of its angles will always be 180 degrees. But if we draw the same, or a different, triangle on a convex surface, such as a part of a sphere, the sum of its angles will be more than 180 degrees. So by drawing a sufficiently large triangle and measuring the sum of its angles, we can determine whether the surface on which we drew it is flat, concave, or convex. Very similar methods are used by astrophysicists to measure the curvature of the universe's space. Instead of drawing triangles themselves, they study triangles formed by nature on the map of the large-scale structure of the universe, which we discussed in one of our previous videos. So far, even the most precise measurements of this kind indicate that our universe is nearly perfectly flat. Does this mean that we can dismiss the theories of a higher dimensional multiverse consisting of bubbles of curved space? Not necessarily. We must remember that we can only measure things within the observable universe, which, as mentioned earlier, might only be a small part of the entire universe. This part could be so small that the curvature of the large universe remains beyond our measurements, much like the spherical surface of the Earth appears flat when we look at the sea. The situation is ambiguous. If we had measured some curvature in the universe, we could say that the whole story with bubbles is very likely. As it stands, we can only state that we don't have any concrete information on this topic. And since we're talking about higher dimensions, we can't ignore what is often called string theory, a theory literally based on the concept of higher dimensions. In short, string theory tries to describe elementary particles, such as quarks, electrons, etc., as vibrations of microscopic one-dimensional objects, strings. It sounds simple, but is actually quite complex. It turned out that string theory can only describe observed physics somewhat accurately if these strings vibrate in more than 3 spatial dimensions, 9 to be precise. If you find it challenging to imagine a string vibrating in 9 dimensions, that's normal. Everyone does. Fortunately, we don't have to imagine it, as we can describe this process mathematically. Therefore, string theory is primarily a highly complex mathematical theory, analyzing the different ways strings of various types can vibrate in multidimensional space and trying to understand the implications. However, even string theory seemed too simple for some, and in the mid-90s, physicists led by Edward Witten proposed that string theory would be much better if we replaced the strings with entities known as brains. What is a brain? It is an object with a lower dimensionality than the space it exists in. A one-dimensional brain, or one brain, is a string. A two-brain is a membrane from which the term brain originates, similar to the skin of a drum. A three-brain is a three-dimensional object, like the drum itself. A four-brain? Well, here we encounter difficulties, as we live in three-dimensional space and can't exist in another. Therefore, we can describe 4 brains, 5 brains, and higher dimensional brains only mathematically. Thus, we have a theory called M-theory, which attempts to describe the entire world as complex vibrations of multidimensional brains in even more multidimensional space using incredibly complex mathematics understood by perhaps 100 or 2 people worldwide. Fortunately, this video is not about string theory, and I don't have to pretend to be among those people or understand it. It's enough for you to understand why in string theory, higher dimensional spaces and objects are not just possible, but necessary for the theory to work. Simply put, if you are a supporter of string theory, or rather M-theory, you must support all these higher dimensional objects and spaces. These multidimensional ideas of string theory fit well into the concept of multiple universes existing in a higher dimensional multiverse, known as brain cosmology. In the most common version of this cosmology, the multiverse is a 5-dimensional space filled with 3-dimensional brains, one of which is our universe. If we imagine 3-dimensional brains as 2-dimensional objects, like pages, the multiverse resembles a book, with each page representing a separate brain universe. According to brain cosmology, 3 of the 4 fundamental interactions, strong, weak, and electromagnetic, act only within the brains, being confined within them like ripples on the surface of water. The 4th interaction, gravity, is not limited to the 3-dimensional space of the brains and permeates the 5-dimensional space of the multiverse, making interactions between brains possible. In particular, brain cosmology includes the concept of an ekpyrotic universe, which suggests that what we call the Big Bang was the result of a collision between 2 different brains, and all the matter in the observable universe is the condensed energy from this collision. According to the ekpyrotic theory, brains occasionally collide, creating new universes, with the parameters of these collisions varying, leading to different structures and even physical laws in the resulting universes. If we could travel through these universes, we might find a universe where the strong nuclear force is not strong enough to form atomic nuclei, a universe where there is too little matter for gravitational collapse to form stars, or even a universe very similar to ours but differing in some significant or minor details, essentially any universe, including those of Star Wars, Harry Potter, or Warhammer 40,000. If this idea of a brain multiverse has inspired you as it once inspired me, I must temper your enthusiasm with some regret. We are not at all sure that any of this is true. Neither string theory, M-theory, brain cosmology, nor the ekpyrotic universe concept is proven or even widely accepted. Many physicists harshly criticize them, especially the ekpyrotic theory, which requires an improbable coincidence of brain parameters to work as expected. So yes, all this might be true, or it might not be. I would even say that, for now, it seems more likely not to be true. Unfortunately, the same applies to all other theories about parallel universes. We are not only unsure if they exist, but also likely never to know if they exist. That's why many scientists consider such discussions unscientific from the start to the end. All we can do for now, at least, is try to find evidence supporting or refuting the physical concepts underlying many world theories, such as cosmic inflation, space curvature, or higher dimensions. Such research could make some many world theories more or less plausible, or even discard some. However, we are unlikely ever to definitively answer this question. But who knows what seemingly impossible things human genius will make possible in the future. Let's hope for the best, dear friends. And on this optimistic note, I wish you all the best until we meet again on our channel.